Hello everyone. Today I'm going to discuss about a very interesting paper which has come out in the last week called Less is More: Recursive Reasoning with Tiny Networks. It has got attention of a lot of AI researchers and people around the world, and rightly so, because this paper has, I think, paved the pathway for building architectures which are customized to specific tasks as opposed to having a one size fits all kind of an approach. So today I'm going to explain my understanding of this paper. How exactly do these tiny recursive models work? And we are also going to look at one example where we are going to apply these models to that example and see whether we are able to recover the accuracy which is mentioned in the paper. Specifically, we are going to focus on this number, which is here 87.4% is the accuracy for applying this method on the Sudoku puzzle. So we are going to see if this number is replicated so that we can develop some sort of a confidence as to whether this method really works, because it's mind blowing to see the kind of accuracy you can get with very small models. So this model has 7 million parameters. Now compare that with something like DeepSeek, which has thousands of billions of parameters. So we have achieved an efficiency which is 10 raised to 6 times that of these larger models, and we are having comparable or even better accuracy. That is absolutely amazing. And I think it really makes a lot of sense because there are a lot of tasks where you might have different architectures which are optimal. So people are so fixated on these LLM architectures that there is very little truly fundamental innovation which has happened in that space. So that is why this paper really piqued my interest, and we wanted to do a video about it at Vijwara. So let's start from the basics, and we will slowly understand what this model is all about. Okay, so let's start with the introduction to LLMs. LLMs are extremely powerful. There are a lot of LLMs out there now. AI labs are coming up with new models every month. We have OpenAI, we have Anthropic, we have Google, uh, we have Grok, we have Alibaba, we have a lot of these companies putting up large and large models which can do so many tasks. They can do a lot of tasks ranging from poetry, mathematics, suggesting jokes, doing complex reasoning, and even symbolic tasks. The range of tasks which these LLMs can perform is simply mind blowing. And that is how they are designed. You ask any sort of question to an LLM and it will give you an answer. And these LLMs have billions of parameters. You pass in any query, the query goes through a gigantic neural network and you get the answer. So there are these computations being performed in every single step of the way. And finally, you get the answer. So to perform these computations, you have these weights of the neural network which are applied to the inputs, and then the output is propagated from the first layer to the last layer. So there are billions of parameters and a huge amount of processing that is required. These architectures are based on the transformer block, which was invented in the year of 2017, where uh, we got really interested in the attention mechanism which was introduced in this paper. And from that point of time, we have discovered that these transformers are truly scalable to bigger and bigger sizes. They scale very nicely. And that's why this attention based transformer architecture became the standard norm of LLMs. And this has been the boilerplate for refining LLMs. We can do a lot of innovations on maybe adding some layers, or even in the post training where we can have chain of thought reasoning, we can have verifiers, and we can introduce reasoning capabilities after the model has been pre-trained. So a lot of innovations going on there, but people are rarely, sitting down and asking the question that these LLMs are designed for a diverse range of tasks, but there are a lot of tasks like coding or solving puzzles. And is this architecture optimal for those kind of tasks? And when you think deeply, you realize that no, they are not. Take an example of a code. For example, a code has a beginning, a code has an end, and a proper syntax which the language follows. Now LLMs are designed to predict the next token, but coding essentially has some set of rules which are inbuilt within the coding language. For example, Python has a specific way of writing the for loop. Now, these rules we are not taking into account anywhere, so it feels like we are using a hammer to kill a mosquito. So, the question is that for tasks which are more specific, like maybe coding or solving puzzles, can we have specific architectures which are not using billions of parameters, but which are more focused towards that specific task, where we only rely on supervised fine tuning? We train on input output pairs, we train a neural network, and we don't really look at the task as a next token prediction kind of a task. In other words, we are going to forget about the traditional LLM architecture, and we are going to think from scratch, because it makes a lot of sense in cases where there are some set of rules which the model has to uncover, and uh, where you might have other architectures which probably have a much better efficiency in terms of accuracy divided by the number of parameters. So that's when I came across this paper, and I really like their thought process. This paper is actually based on another paper, uh, which is heavily referenced in the initial 3 4 pages. So in this lecture, I've tried not to reference that work because I'm aware that many of the listeners would not be aware of the first work, which is called as HRM, hierarchical reasoning models. So I'm going to explain everything from scratch. But you can think of this work as a second work which has come up in the line of these recursive models. We are also going to understand where does the word recursive come from. The first impression I have when I hear recursion is that you pass an input through some processing block, you get an output. You pass that output again through the processing block, you again get an output, and you keep on doing the same thing again and again. So essentially, you can write this down as probably something like x of t plus 1 equal to some function of x of t, where t plus 1 is the next time step and t is the current time step. So these are some of our initial understanding about recursion, and today the main motivation is that we are going to look at an example of a Sudoku puzzle. So Sudoku puzzle has a fixed set of rules. For example, in this horizontal line, you need to have all numbers. In the vertical line, also you need to have all numbers, and you cannot have the same number repeated twice in the same line, etc. So there are some predefined set of rules which our model has to learn, but LLMs don't seem like a optimal way of handling this task, because it seems like an overkill, where we are generating one single token at a time, and even if one token is incorrect, it can render the entire answer to be invalid. So from that point of view, we are not going to look at traditional LLM architectures. So let's take an example of a Sudoku puzzle which has a fixed set of rules, and we want to develop a model which can take this puzzle as an input and give me the solution as an output. So the first question which might have come to anyone's mind, if imagine LLMs were not introduced at all in this world, then how I would think of this is that you take a neural network, you give inputs, you give outputs, and then you help the neural network learn the mapping between the input and the output. So it's a black box, but you are hoping that the black box is getting more intelligent with time. So essentially, you are building an intelligent black box. So we are going to do something quite similar, but we are going to introduce two new ideas on top of these this neural network paradigm, um, which is the first approach which comes to our mind intuitively. Okay, so if we think of solving this Sudoku puzzle from scratch, we understand that as humans we do a lot of trial and error before we get to the final answer. We try different things, and then that doesn't work out, we again try. So there is a lot of trial and error. Or uh, let's say we go ahead with approach 1, that doesn't work out, we move on to approach 2, that doesn't work out, we again proceed to approach 3. So it's like we are doing a lot of iterations before we get to the final answer. So throughout this lecture, these iterations, I might reference them by reasoning or latent reasoning or chain of thought reasoning. But essentially, when you hear me saying all these words, just think in your mind that it's nothing but a human sitting down and trying to reason about, okay, what's the next step? Will this work? Will this not work? Essentially, it's a trial and error step. So now let's look at how can we tackle this problem without being biased by the LLM architecture. Okay, so let's look at the three steps which have been proposed in this tiny recursive model or TRM paper. Step one is called as recursion to improve reasoning. So, what does this step mean? Let us try to understand. To solve a Sudoku puzzle, you'll first sit down and think, okay, fine, let me try this first approach. Then you realize, oh, that doesn't work out. Let me try this second approach. So you will do some amount of iterative reasoning so that your reasoning before you get to the answer improves. So this is exactly what we are going to do as the first step for the tiny recursive model. Now, one question which might come to your mind is, okay, fine, I'm talking about these different approaches, approach 1, approach 2, approach 3, or iteration 1, iteration 2, iteration 3. But how am I going to go from the previous iteration to the next iteration? So we need to have some model at the core, right? Which helps us improve from the past iteration to the next iteration. Now, I'm going to show this model to you in an animation. So let's look at these two layers for now. So in this model, what we have is we have two distinct layers. This is layer 1 on the left, and on the right, what you see is layer 2. Within each layer, there are different blocks. So there is an MLP block, which is a multi-layer perceptron, and there is a normalization block. People familiar with the transformer architecture might be familiar with both of these names, but it's a standard. MLP is just a neural network, and normalization layer is an operation which normalizes the weights of your network. So you are applying these blocks multiple times in two layers. To give a context, LLMs have a lot of these layers stacked one after the other. Usually they are around 90 to 100 or even more. And they also have an attention block sitting inside all these boxes. But we have not shown the attention block here in our example. Okay, so now what happens is that this is our model. And what is the input to the model? Well, there are three inputs which are fed to the model. The first is the question itself, which is this question which you are trying to solve. The second is your prediction, which can be any initial prediction. We can even randomly initialize the prediction to start off with. And the third is a variable called z, which is also called as latent reasoning in the paper. So it's essentially like a chain of thought before you get to the final answer. So what does the chain of thought look like? Something like, okay, this is the input. So let me go ahead with this as the step one. Now I'll do this as step two, etc. So what you do is you take these X, which is the input, that's the question that's known to us. Y is the initial random guess, which is the prediction, and Z is the reasoning, which is also very random initially, by the way. We have no idea what Y and Z are to begin with. And then all of these we pass through our network and we get an output from the network. So this one step we are going to do multiple times, and this is what is called as recursion in the paper. Recursion means that we are passing these three inputs multiple times through the network to improve our latent reasoning. You can see this update is only connected to the Z, which is the reasoning block. It's not connected to the answer or the question, it's only connected to the reasoning, which means that let's say we fix our prediction and then we are iteratively improving our reasoning 1, reasoning 2, reasoning 3, reasoning 4, etc. We do it number of times, and then this is something which is done without uh, back propagation, which means that we are not going to update the weights of our network after all these calculations. So we disable the backward propagation for this recursion step. I'll explain why that makes sense. But in this first step, we are only running the forward pass for n number of times, where n is the number of recursion that you want to perform. So latent reasoning can be simply thought of as chain of thought. What we are essentially doing intuitively here is that we are improving the chain of thought that leads us from our question to our prediction. And that's why we are doing it iteratively number of times. So this is explained in this paper in this algorithm, which they mention in this small block, which is figure number 3. And what we are doing here is just this, which is improving our latent reasoning by iterating recursively for 6 number of times. Now, a very logical question that might come to your mind is that why are we only improving the chain of thought? We should improve the answer also, right? Because finally the answer is linked to the chain of thought. And that is exactly what we do in step number 2, where what we do is we again pass this updated Z and the prediction and the input through this network, and then we update, this time we update our prediction, and this is only done once. And this you can see clearly mentioned here, where we are refining our output answer. Okay, so now this is step number 2. Now step 1 and step 2 essentially are doing recursion and updating the final answer. The next step in the algorithm is to do these steps multiple number of times. So this is done in this middle block, which is called as deep recursion, where you again recurse through this for a total of t minus 1, where t equal to 3, which is 2 times. So essentially what you do is that you perform step 1 first, then you perform step number 2, and then you do it, you do step 1 and step 2 2 times again. So that's why it's called as deep recursion. And the intuition behind it is just to refine your latent reasoning and your prediction uh, before you go ahead and run back propagation, which I'm going to show in the next step. So essentially, what happens is that you're updating your neural net, the weights of your neural network, not for these two steps, but essentially only for the last step, where these improved reasoning and predictions are being passed again through the network, uh, and then it's being compared with the true prediction, and we are running a backward propagation in that step. So just to summarize, what we are doing is that we have an input question. We have a target answer also for that input question, but we are not looking at that. For this input question, we have a predicted answer and latent reasoning, which is denoted as Z. The first step we do is that we iteratively improve our latent reasoning by running through the network multiple times. Then we improve our prediction based on that improved latent reasoning, and then we do this multiple times to improve our predicted answer and the latent reasoning as well. Now we have covered step number one and step number two. So you might have this question that, okay, so what is the loss, right? Like how do I back propagate through the network? How do I improve my weights to reduce the loss? So we are now coming to that. Since we have improved the prediction, the last step is to compare the updated y, which is here, and the true y, and uh, apply a cross entropy loss to minimize the difference between the updated prediction and the true prediction. And this is what is called as deep supervision in the paper, and this is one of the key innovations which is highlighted along with the reasoning. And the reason it's called as deep supervision is that we do this back propagation for a number of steps, as you see in this algorithm. For step in range of n supervision, which is 16 in this paper, so we run through this 16 times. And what that means is that it's like we are emulating a neural network which is very deep, even though this is not a very deep neural network. But because we run this deep supervision multiple times, essentially what we are doing is that we are passing our input through a very deep neural network. So we are emulating that network. And this is something which I found to be very interesting, because if you do not include this deep supervision step, you do not get an accuracy which is comparable to these larger LLMs. And then these are the only three steps which are included in the tiny recursive model, or TRM. So the reason that I am very excited about this is that you can understand about this by only understanding about neural networks, even if you skip the LLM part completely, because we are thinking from scratch here, and we are trying to solve a very specific domain here, which is Sudoku puzzles. And okay, fine. So these are the three steps, and this is how the architecture is built. So let's look at steps again. So step one is you pass XYZ through this block. You iteratively improve your latent reasoning, and you do this for number of times in the first step of your algorithm. Here you do not have attention block, which I have mentioned here, but in the paper they have explored different architectures where they have added this attention block as well. For Sudoku puzzles, they ran an ablation study where it turned out that adding attention block performs worse than just keeping an MLP blocks in the architecture. So that's why I have only included these blocks in the architecture here. And then in step number two, you update your answer. You update your prediction of the answer, because this is what will be used to back propagate and to basically match with the true prediction. So essentially you are first running this, the first step, then the second step, and then you do it again number of times, which is called as deep recursion. The first innovation in this paper is the idea of recursion, which I don't think is truly unique, because the same idea is used in RNNs or recurrent neural networks. but still, using it for solving complex reasoning tasks is quite interesting. And then the last step is where you compare your updated prediction with the true prediction and perform a cross entropy loss, back propagate, and update the weights. Now, these are the three steps which are involved in the tiny recursive model, and then uh, that's all. These are the three main components. There is one piece of the puzzle which I have not really highlighted here, because I don't want to take your attention away from the true building blocks. But that important piece is mentioned over here, which is called as adaptive computational time. So, as I mentioned before, in the deep supervision steps, you run the loop for 16 supervision steps. However, it's not very optimal to run each batch of training data for 16 times. So, what they do is, if you, let's say, match the true with the predicted, then uh, you stop the loop there. This is what, so in this step we are calculating the loss using the cross entropy of y hat is the predicted and this is true. This is what you see in this figure, but there is a line which appears below that, which is binary cross entropy. What this line means is that if y hat, which is our prediction, matches the true, then basically you're halting the loop. You don't want to waste any more computational resources, and then basically you break the loop in that case. So this is another small intricacy which is added to the paper to improve the computational efficiency of your algorithm. Once you have assembled these building blocks together, you can actually run the training, and then you can help the model understand the pattern of uh, predicting the output given the input. And to understand this pattern, you need to train this neural network for multiple time steps so that you eventually get to a decent accuracy where you're sure that this neural network has actually learned to solve Sudoku puzzles in this case. Okay, so now the last step, theory is has its place, but unless you really prove that something works, there is no real fun in the whole process, right? So in this last section of this lecture, I'm going to help you understand how to run this model and check the results for yourself, so that you really get a feel of what we are trying to do here. So this is the repo, which is released by Samsung Sale Montreal. And interestingly, this paper is a single author paper, which goes on to show that a single person can really do something uh, impactful in the field of LLMs, where you have these giant resources being poured out by AI labs all over the world. Okay, and then you can see that in just 5 to 6 days, this repo has reached around 4K stars with around 500 forks, etc. So it has become massively, uh, I would say, viral, just because using a very small model you are achieving a high accuracy. But again, let's first prove it ourselves so that we can get confidence. So the first step for you is to clone this repo and then run these installation blocks which are mentioned in the website. Please also connect your WarnDB, because it allows you to visualize your training results so that you see what is the accuracy you have reached. For me, this step took quite some time, because there are some installation which are compiled from source, so it takes around 10-15 minutes. And then in step two, basically you build your Sudoku data set, you divide it between into training and testing. And in the last step is where you run the training loop. And here you mention number of epochs as 50,000, learning rate as 10 raised to minus 4, um, number of layers are 2, and we are using an MLP architecture here. It doesn't have an attention block inside. Okay, so the data set is Sudoku Extreme, which looks something like this. You have a question and then you have an answer. So we are training our model to develop a mapping between this question and answer. And then what is mentioned in the repo is that you need GPU for this. So I use this L40S GPU on RunPod, and I ran it for around 24 hours and I got my results. So it costs around $20 for you to run this code. And then the results you can see here, the loss decreases with the number of steps. What I'm mainly interested is in this accuracy, which I got to be around 88%. And let's look at the accuracy which they mention in the paper. So in the paper, you see the accuracy comes out around 87.4, which is quite comparable. And this is, however, the test accuracy. And what I have mentioned here is the training accuracy. The test accuracy appears, so these are the training charts. The test accuracy appears over here, which I got to be around 70-80%. So slightly less than what is reported in the paper, but still seriously impressive with such a small model. So my conclusion and verdict is that it works, and whatever they have reported in the paper, the numbers, um, they are accurate. It's easy to run. It takes somewhat more time and it costs around $20. But the satisfaction that you get at the end after running this paper is incredible, and it opens the pathway for doing research on your own also, right? For example, there are a number of ideas coming in my mind right now after I have understood this paper. But what I'll recommend all of you after seeing this lecture is go ahead and print a copy of this paper and read it by yourself. It's not a very difficult read. It references a lot of this hierarchical reasoning model, HRM. So I did not read that paper, but I understood the building blocks of this paper properly. And then I really encourage all of you to replicate this paper. Thank you so much, everyone. I hope this was useful, and please let me know in case you have any doubts or questions. Thanks.